And yeah. So they can have some water. Yeah. Have you guys seen this before? Do you prefer the whole of it in one screen, or do you want to break it into two? Is this readable? Maybe I could put it on. Maybe both boards. Yeah, both boards, but I'm saying, do you divide this into two? No, right? No. Okay, and it was readable? Yeah. Okay. So let's see. Yes. At least once.
He's on his way. He'll be here
Oh,
in
okay.
just
Yeah.
like-
No, I didn't intend to disturb him. Maybe he wants to be absent. Should have given him that luxury, right? A lot of physics. Okay. Oh, yes, please, please, please. Let's study.
Thinking number 3, I'm implication. That's why I have right, but we can discuss about that later. I am not for that. Sorry.
Okay. Is all the process clear? Any questions from what we did online last time? Good to see you guys all, like face to face. Yeah, I saw you in the corridors, but it's good to see you. A little more and closer. Yeah. So I'm Shadish again. I think most of you know. I think Puza and Pradeep. Yeah, I think again not here, but okay. And there's a homework due on Thursday. So homework on you. What's the date? 30th, I think.
Yeah, it'll be 30 minutes, right? Tuesday.
Tuesday. Homework 2, I intend to post today. Can I make it due February 1st? Maybe. I'll start today itself. Okay. If we cannot, then just so that we can catch up on what we missed last time. If we cannot, we'll be a little flexible with that. Okay. So I usually do one lecture on forces that depend on position, another lecture on forces that depends on velocity. I'm going to skip the forces that depend on the velocity. That's a homework. Both the homework problems are related to that. And I also give a quiz where I asked you to calculate the time it takes for a ball to go up and come down in the presence of drag. Right? If you do that satisfactorily, to my satisfaction, then that's an additional bonus. You have all the time for that. Take your time. Let's put a rough deadline of midterm 1. Okay, midterm one, when is midterm one? I don't know. Midterm one is February 25th, 22. Okay. That's a Tuesday or Thursday? Thursday maybe? One, yeah, 1 plus 14, or 1 plus 21 is 22, right? Yeah. So, okay. So before midterm one, maybe you have to work that out. If you don't work that out, you don't lose anything. If you work it out, some bonus, I don't know how I'll decide the bonus. The easiest thing I can do is replace the lowest homework that you have. That's one thing. Another thing I can do is I can do something with the midterm, but let me not go there. It depends on how the work is. If it is not satisfactory that I can include the exam, then so for now, let's try to give a bonus on homework and then later on. Is that something? Is that clear? Any questions on that? So today, I want to proceed and do something on what is broadly called calculus of variations. Have you heard of the terminology? Calculus of variation. What is it about? Anything? Well, ideas, languages, or keyword is calculus of variations, I think.
Dealing with the uniform.
Yeah.
So finding the area underneath the curve.
Correct. And maybe you want to say something more? Yeah.
It's also thinking, well, surface area can also be calculated by the integral. Surface area being surface can be calculated by the integral. Well, it's volume.
But that's an integral, right? You
Yeah.
use standard integrals for that. Calculus, so calculus has derivative integrals. Integral will help you calculate the surface area volume
Yeah, as well as the volume.
and
Surface. Okay.
Yeah.
And also partial integration too.
yeah,
Is a so integration of in X, Y, and Z space.
yes, all that will be integrals, I would say. Integrals and multivariables, maybe.
Yes. Yes.
So how would you say
Integration
calculus of variation, something very, what comes to the striking thing about calculus of variations?
graphs as well.
No. No. When it comes to Lagrangian, have you guys must have heard of the word Lagrangian? Lagrangian mechanics, what does it do? If you had to explain Lagrangian mechanics to, let's say, to me.
That's the kinetic energy and potential energy of the system.
Yeah.
System.
So more,
Can be represented into a matrix, a system of linear equations.
more. I'm trying to get this piece out of you. All that is correct statements, but I'm wanting something very specific, very crucial, something very fundamental. What's an action principle? Is that a familiar idea? Action principle? No. Or maybe let's state it in more physical terms. Lagrangian is very similar. If I tell you that I have a water droplet, okay, it can be of any shape, like when it falls from the cloud to the ground. What's the shape of a water droplet? Any idea?
If you like teardrop.
Teardrop, probably, right? But true. But let's say, what is the shape? Suppose you want to investigate, and then you say that, okay, that's too sophisticated way of saying it. Let's say, mathematically speaking, I have a fixed volume of water. let's say 1 milliliter, right? And then I say that it can take any shape it can, it's not even under gravity, it's in vacuum, but I say that it has to have the least surface area. It can turn around or it can be squeezed, everything, but I want the particular shape that has a least surface area. Okay, volume has an integral, surface area has an integral associated with it. So this becomes a problem of keep this fixed, and this should be a minimum. It's not just anything. I want to keep it minimum, right? And that leads to the maxima minima problem. How do you find a maxima or a minima of a function? Like
Variation.
variation, yeah, something.
So,
Yeah, you'd say derivative is like if I have a function, like a maxima minima, so that's 2. So if I have x and this is f of x, if I want to find the maximum, at least local maxima, that's derivative is 0, derivative is 0. But the only difference now is that this is a very similar statement we are saying. I want the surface area to be minimum, keeping the volume fixed. Surface area is a function eventually, but it is coming as an integral. Right? Lagrangian is written as an integral, right? Integral of the Lagrangian is the action. Is that a familiar idea? Integral of the Lagrangian is the action. And then we say that we want to minimize this. Like we want to minimize the surface area. So we want to find that derivative. But now the function is not a normal function, it's an integral. So that's a complication, right? That the function is not just x squared or sine x or a simple function, it's written as an integral. So we want to minimize an integral. So that's what we want to work with. That's what is called calculus of variation. It came right at the time of Newton itself, or Newton gave calculus, or at least made it very clear how to work on calculus, and right immediately, I think it was Bernoulli who first phrased a problem in this form. Again, have you heard of brachistochrone? Is this a familiar word? Brachistochrone. Oh, this doesn't show up there. See? What's the brachistochrone? What's the brachistochrone? Never heard of it?
Is it come from bracket relation something or different? It's coming from the bracket relation and
No,
this is
no,
different.
no, it's a shape. Brachistochrone is a shape.
Oh.
It's a shape, it's a geometrical shape. You're not familiar.
Yeah.
Gateway to the West in St. Louis. Familiar with the word? You're from St. Louis, you should know. What's the gateway to the West?
The hyperbolic cosine.
Very good, very good. So you're familiar with the arch, or you'll call it the arch,
Yeah,
arch,
the arch.
arch in St. Louis, familiar? No? Yeah, that's okay. But you were in Illinois. Hey, you're not very new. In St. Louis, there is an arch. Might have seen it. Think about it. What comes to your mind when you say St. Louis? Uza, are you familiar?
Because I came there in the night.
Seen that arch.
Yeah. So St. Louis pictures, you will see an arch like that. Yeah, that's not just an arch. Like it's a, what's the technical word for that, for the geometry?
Hyperbolic.
That's a hyperbolic cosine, that's correct, very good, but the more common word? Catenary. That's I think so at least. Okay, correct me. Yeah, that's the same shape.
X squared, because nothing can be really.
It's not parabolic, yeah, it's not x squared. If you see power lines, like hanging around the two poles, what's that shape? It's not parabolic, it's cosine hyperbolic. That's the same shape, this is inverted. Okay, so St. Louis arch has something mathematical associated. with it. Okay. What's so special about that? Like, again, it is minimized. It could have taken any shape, right? Under gravity, energy is minimized for this power. Right? Any shape that will minimize the energy is what will go with it. So that's the idea. And Brachistochrone is the following. Let's say you have an inclined line, you roll so this is nicely having friction on it. When you have nice friction, things roll very well. Right? If you're driving on an interstate, if it is snowy, then you start spinning, you get stuck. If it is icy, it is hard to roll, it slips, right? But if everything is good, if it's a good weather, then your tires roll very well, right? So if you're perfectly rolling, then you start from here and you reach here. That's the goal, let's say. And it will take a certain amount of time. Agreed? There is also a possibility that you could do this, right? Still it will roll, right? It might take a different time. Okay, you can do this. It will take a different time. But you ask the question that out of all these curves, so there is another possibility that you teacher probably won't cross that, right? So let's say. So let's say like this, because otherwise you won't cross that. Or if I start from rest, it will cross. All this, I can go very deep and then come back here. And you will argue that, oh, it's picking up so much speed that maybe this is better, right? Because it gets really fast. And then you ask, what's the curve out of all this, which takes the shortest time to reach? Okay, and it is not the incline. It turns out that it does go dip a little and then comes back. And that's a Brachistochrone curve. That particular shape is a Brachistochrone curve. If you're not seeing this, you saw the old graduate offices, like on the 4th floor, there was a oh, how do you call it? A balcony kind of area where you could see the parking lot.
Okay.
Right, that's a 4th floor. You can even now go there. I think a couple of you probably have offices there. Right underneath that, there is a 3rd floor, of course, right? That's a mathematics library. Like there are some small toys there, right? You can do this setup there. So they have this shape drawn there, and you can have metallic balls there. You will roll it, and you will see that it reaches first on this curve. So that they have about 3 shapes in there, and you start the 3 balls there, and you reach. Quiz, right? Write something about Brachistochrone and Bernoulli. How is Bernoulli related to Brachistochrone? So that again, I can tell the story a little bit. It's kind of a good story to narrate for you guys. So this, so the idea is that Bernoulli came up with this problem. He phrased the problem and he put it in those. I think he communicated it to all his friends, and Newton was also a colleague of his contemporary, and he sent it to everyone, asking that who can, and he's made it anonymous, I think. Something like that. And Newton, now that we know a lot about Newton, all his paperwork, correspondence and all, apparently he solved it overnight. Gave the problem and he solved this problem overnight. What is that curve shape of that curve? So it is Bernoulli who did it first, but it's good to realize that Newton was good enough that he did it. Okay, we want to be able to address these questions. We want to be able to derive, so that will be one of your homework problems, that you calculate what the Brachistochrone equation is, catenary. Those are all classic problems which you should do. And here we want to develop a machinery for that. And eventually, the idea is that Lagrangian, we're going to minimize the action, not the Lagrangian. Integral of the Lagrangian will be the action. And when you minimize the action, like when you minimize time here, you get this curve. Correct. When you minimize the action, which is the integral of the Lagrangian, what do you get? No, there's something more physical. Like here, if I minimize, I ask the question, how much time does it take to go from here to here? And I ask which curve minimizes this time. That's a curve, equation of a curve, that's a Brachistochrone curve. Now, I'm now telling something entirely different. I'm using a jargon here, that action. I haven't introduced you action. But the idea is that somewhere else you're seeing the word in an undergraduate course. Action is the integral of the Lagrangian. We'll see that again here. So action is if you minimize the action, whatever that means. Okay. You will get something. Here you got a brachiostogram, but now you're minimize that action, you will get something. That's a curve actually. It's the curve for what does minimization of the action give you?
Yes, minimum time.
No, it's action is not time. So we are not minimizing the time, right? We are minimizing the action. It gives you Newton's laws of motion. That's a big deal, right? Physics is managed by Newton's laws of motion. What Lagrangian principle says is that there is something more fundamental, or you could think of it as something more fundamental than Newton's laws of motion. That is an action, which is a Lagrangian, integral of the Lagrangian. You minimize the action, you get Newton's laws of motion, right? That's a very big statement. And that's the
So yeah, the Lagrangian is equal to the action, then if you minimize the action.
action is the integral of the Lagrangian.
Okay.
So you minimize the action, you get Newton's laws of motion. We'll see this. That's what this whole course is. A good part of this course is going to be. So we have to learn to minimize things. We have to learn to minimize integrals, and that's what. So let's go back and do something very simple. To change Fermat's theorem. Is that what's called? What is Fermat's theorem? There is a lot of theorems associated with Fermat, so it doesn't help. Fermat's theorem. Snell's law, maybe. Snell's law should be more familiar. Angle of refraction. Right. That's that is and when you say it as Fermat's theorem, you say that light goes from one point to the other point in such a way that complete the sentence. It changes its path to
the normal line.
That is right. That's the way we study refraction. But I was saying Fermat would say it the following way, that light travels from one point to the other in such a way that it takes the shortest time to reach there. For some reason, light already knows that that's the shortest path. That's again remarkable, right? So Snell's law is like Newton's equation. That's what we use. But you can state it in a different way, that light takes the shortest path, it takes a path which takes the shortest time. So if I do that, I'll get Snell's law, right? Again, notice if I minimize action, I get Newton's law. So if I use Fermat's theorem, I'll get Snell's law. So that's going to be our statement. So let's do this in a very first. We want to do this as an integral, but let's do something very straightforward. So let's have a rectangular region, and let's say I don't think it matters. Let's say this is x0, that's x1, and that's x2. And my goal is that I start from this point here. Let's call that x0, y0. That's y, right? Y is in the vertical direction. That's x0. And I have to reach somewhere here whose coordinates are x2 and y2. So I don't give a choice as to these 2 points are fixed. Okay. And This is of course going to be worked out with light. Let us say I have this to be concrete, so I'm changing the problem a little bit. I'm really walking. I have a park, and part of this park is laid with concrete, and the other side of the park is sand. Right, and we can walk faster on concrete than sand. All of, at least normal people can walk faster on concrete than sand. And that means, and then our goal is to start from here and reach that. And which path should you take so that you reach in the shortest amount of time? Okay, that's a question I ask, and you would say that, oh, I can go faster here. So you would say, oh, maybe I should spend as much time as I want there. So that's here. And again, on interstate, we do the same thing, right? That is an interstate. If you're going from here to St. Louis, you can take 64, Highway 64, which is much faster, right? Or you can take a road, internal roads, which is slower, but then it's a shorter path. 64, you have to go to Marion and then come back, but then you can go faster on interstate. So you have to play a dilemma. Oh, you go here, I get a faster velocity. If I go here, I get a far shorter distance. Which one is better? So there's a bargain, right? Same thing. This is going this way, but then if I go straight line, we always know that it is the shortest path, but then you're spending more time here. So probably somewhere in between is where that bargain is, right? And the question is exactly where do you have to go, right? So we want to find this point where you have to go. So this is a straight line, and then again a straight line. And let's say that's x1, y1. So the question is, what should that y1 be? I have fixed my x1. There's only one possibility I have, one choice I have, and that's y1. Right? So the question is, for what y1 is the time taken to go from x0, y0 to x2, y2, a minimum. Often you don't say minimum, it can be an extremum, sometimes it's a maximum also, but at least in this problem, it is the minimum. Okay, is that question very clear? Right, at least the phrasing of the problem, is that very clear? Any comments, questions on that? Good. Okay, so how do we set this? I have to give some velocities now, right? Let's say we can go with velocity v1 here, velocity v2 here, and v1 is greater than v2, right? That need not be always the case. And so I spend time t1 here, so let's say time taken is, so the total time taken, there are two pieces, t1 plus t2. Time taken to go from here to here, then from there to there. And time taken for t1 will be distance by velocity, right? So let's say this is s1 over v1, where s1 is this distance here. That's s1, right? And that's s2, that triangle there, plus s2 over v2. Okay, clear? I want to minimize this. So this time t, it has only one variable here. It's a function of y1. So let's say more concretely, ty1 is equal to 1 over v1. v1 is fixed. s1 in terms of x0 and x1, that's the difference between these 2 points, right? So it is x1 minus x0 the whole square plus y1 minus y0 the whole square. Okay. Plus 1 over v2. The distance between these two coordinates is x2 minus x1 the whole square plus y2 minus y1 the whole square. Very clear, right, what we are doing. I want to minimize it. What would I do? Take the derivative, right? There is only one variable y1. I take the derivative, set it to 0, right? So minimum m implies that partial derivative with respect to it has so many variables. Take the derivative with y1, set that to 0. That equation will give me a particular value for y1, or that's an equation, and that equation decides what that minimum time will be. More than the minimum time, I want that equation, right? This setup is what we are interested in. Clear what we are doing? So take the derivative, right? So take the derivative with respect to y1. All these are constant. It's only this y1 that comes in. When I take the derivative of a square root, it's 1 by 2 minus 1. It goes in the denominator. So that's 1 over v1. That is a factor of half. That's a power. And this goes in the denominator. x1 minus x naught, the whole square, plus y1 minus y naught, the whole square. And I have to take the derivative of the argument. This is not having y1, it has y1 here, so it is 2 times y1 minus y naught. Right. Do the same thing here. I get 1 over v2, that is a factor of 2. I get 2 times y2 minus y1 over x2 minus x1, the whole square, plus y2 minus y1 the whole square. And what am I missing? Minus. Very good, right? So this is the minus, right? Because the argument here has a y1 has a 1 minus 1 in it, so I have to put a minus sign in there. Okay, good. The denominator here is nothing but s1, right? Factor of 2 cancels out, so this is nothing but y1 minus y naught divided by s1, and let me also say that is a 1 over v1, right? 1 over minus of 1 over v2 y2 minus y1 over s2. At this stage, let me change the idea of the problem. I said we are walking on a concrete and sand. Let's say this is glass, this is water, and in glass and water, the speed of light is different. We asked the same question, how much time does it take to go from here to there? But now it is not me walking on in a park, it's light going through material. And instead of v1 and v2, what's the characteristic of a material that depends on the velocity inside that material? Speed of light in a medium. What's the property? Refractive index, correct? Very good. So refractive index of a medium is C over V. Correct? That's how you define a refractive index. It's always, is that correct? Yeah, it's always greater than 1 because V is always less than speed of light. C is the speed of light in vacuum. So it is always greater than 1. So let's call this N1, that's N2. I want to incorporate that here. So I'm going to multiply this whole equation with C. So I write, instead of taking the derivative with of time, I multiply by C everywhere. The only thing I did is multiply by C everywhere. Is that clear? So I'm minimizing C times T, that's all, but C is the constant, it shouldn't. And then I suddenly realized that, oh, that's N1 then. N1, Y1 minus Y0 over X1 minus N2 times Y2 minus Y1 over S2. And we can set this to 0 if we want, because we are minimizing it, right? But what is Y1 minus Y0 over S1? So let's look at this a little more closely. Let me redo this diagram. That's it. Somewhere here is my X1, Y1. That's X1, Y1. And so geometrically, Y1 minus Y0 is this distance, right? Y1 minus Y0, and that's S1. This is Y1 minus Y0. If I were to do this over the hypotenuse for a right triangle, what is that equal to? Right? That's a sine of the angle, right? Opposite. So if I were to have this angle here, it's Y1 minus S1 is Y1 minus Y0 over S1 is θ1 here, which is the same as this angle here, θ1. If you think of refraction, that's the same angle that we talk about with respect to the normal. So this one here is N1 sine θ1. And the other one, Y2 minus Y1, is this distance here, Y2 minus Y1, S2 is this. So the other angle is θ2 here. So that's minus N2 sine θ2. Set this to 0 because I want to minimize the time. Fermat tells us. So Fermat does not talk in terms of Snell's law. Fermat says that light travels in such a way that this time is minimized. If this is minimized, this must be true. So this is a consequence of that fact, which is Snell's law. That's Snell's law. But see the difference in the statement. We are saying Snell's law is a consequence of the fact that time or the light is traveling in such a way that time is minimized. It somehow knows what is the, like even before it started from here, it knows that it has to go that way. Like typically, unless you go through a way, you don't know which path is the shortest one. So in that sense, nature is trying to minimize something. So you're saying nature somehow has a fundamental principle that it is trying to minimize. And similarly, we are going to show that. Come on. How does it know? So that's what the principle is. That's a law, right? So when you say that action principle, so it's called stationary action principle. So you say that somehow nature, quote unquote, like magically knows which path to go. That's the law, right? We don't know how to explain that, but it's the same thing with Newton's law, right? You don't say, oh, how does this equation say a differential equation know beforehand, right? So that's the theory that, okay, if you write this differential equation, the trajectory is that. But now we are giving a little more meaning to that. We are saying that that trajectory is in such a way that it takes the minimum action. It's not the time. Action doesn't have the units of time at all. Lagrangian has the units of energy. Time has the unit of seconds. Energy times seconds. What is that? So just for action, we will write it as W is an integral in time of Lagrangian. Lagrangian has kinetic energy in it, energy, time. So this is joules second. So action has a unit of joules times second. What physical quantity that you've studied in mechanics, undergraduate mechanics or very elementary mechanics has a unit of joules seconds? That's energy per unit time. Over time, good, but it is divided by time. So here we are multiplying by time. That is a physical quantity you will associate with. Action has the
Planck's constant, each one.
very good. And so what's the unit of Planck's constant? So apparently you're suggesting that that's good, very good. So Planck's constant has the same unit as joules times second. But Planck's constant is a constant. So tell me something that you study in elementary physics, like Newton or force or momentum or something like that.
Impulse.
Impulse will be force times second. So it is Newton second, yeah. The joule second. That is something. Huh? Sorry? What? No, what is what Nahida was suggesting was joules over second.
Efficiency of powers.
Efficiency will be dimensionless. Efficiency is something divided by something now. Or try. Is something elementary that you study in the first course of physics.
To power or something?
It's coming something with force. I mean, joules and seconds. I cannot tell you better than that. I think power is probably, I would say no, but then everything is connected. So I would say no. You're going the wrong direction. Because you want it in the numerator.
Energy.
Energy is joules. So you want to multiply by to time.
That's called energy times time.
List all the physical quantities that you studied in your.
It's like
Yeah, tell me, yeah. Let's see how far you can go.
work done.
Force.
Okay, you start with time, position, velocity, acceleration,
Moment.
mass, force, energy, and then what? Then you come with power and then
Moment.
momentum, but that doesn't have. The torque. Yeah, now you're in the right direction at least, but it's not torque. Torque is Newton meter. It's joules. By the way, torque and energy have the same units, is that correct?
Is it moment of linear momentum?
Moment of linear momentum, and that's called very good. Huh? That's called? There's a word for it.
Angular.
Angular momentum, very good. Right, momentum, very good. So that's the technical word for moment of linear momentum. That's angular momentum, h bar, the spin, like spin. Most of you do. You're in quantum mechanics. What's the unit of spin? What's the unit of spin?
H bar over 2 pi.
So h bar, right? So h, it's angular momentum. Right? Spin is the residual angular momentum in the rest frame. Right? So that's joules per second. So action has the unit of angular momentum. So what are you minimizing? So apparently you're minimizing the angular momentum of the system. Like, okay, like that's not the right way. Action is action as a unit of angular momentum. It's not really, or I don't know. That's a unit of angular momentum. Action is action, right? It's not angular momentum, right? It's Lagrangian. So, and it turns out what you'll study is that, or we'll see in a few weeks, is that you minimize that, you get Newton's laws. Right? So same thing here, same what you get Snell's law is sufficient to work with refraction, but Fermat takes it in a different way. When you say that light goes in the shortest path possible, that's more deeper in a sense, right? But still, as far as the application goes, Snell's law is good enough, right? So same thing, Newton's law is good enough. In fact, Newton's law is much more powerful than Lagrangian mechanics, but at a fundamental level, it has more depth in it. For example, if you have to work with kinetic or kinetic friction or static friction, Lagrangian is not a good idea, right? Anywhere there is a dissipation, Lagrangian is probably not even possible to do it. So Lagrangian, you will never see people who make bridges work with Lagrangian. You don't, right? There it is necessary that we introduce normal forces, we introduce tension forces. Those things cannot be handled with Lagrangian very easily. It can be probably, but with a lot of much more infrastructure than we want to. So it's too much work for that. It's dissipative. It's not. So if it's not dissipative, conservative forces, what are the conservative forces? Gravity, electrostatics, magnetism. Those forces are very good with Lagrangian. So that's what we will do. So fundamental forces is what Lagrangian is good with. Okay, so that's good, but this is too simple, right? I said we will work in calculus of variation. This is not calculus of variation at all. This is maximum minimum. This can be done at an elementary calculus course. Right? But now what we want to do is, this was very distinct, right? This is like N1, N2, this is discrete, right? N1, N2. Have you heard of the physical phenomena called mirage? Mirage? Yes, what is that?
The range surface, when it's a sunny day, we can see if we are in the very far and we can see the like a water in the road.
Very good, right? So this is mirage. And mirages, basically, usually you say this is ground on a hot surface, on a hot day. So this is hot. Like typically, on a hot day, a concrete surface or a road gets hotter than the air around it. So this is very hot. So as you get in this direction, this is cooler, right? So this is hot, cool, relatively, even a little above it is cool. And refractive index is temperature dependent. Okay, refractive index that we say of air. What is the refractive index of air? One, right? To 2 significant digits is 1, right? If you go to 4 significant digits, 1 is also vacuum, right? So if you go to 4 significant digits, actually that's a 1.00 something there. So it does have some refractive index, and the refractive index is increasing as a function of height. Let's say in that direction, right? Height. It is increasing. So this is no more a discrete system, it's a continuous system. Right? The refractive index is continuous. Right, the same idea, but it's continuous. And now light comes. Let's think of it as layered system, though. So this is air. So that's your layered system. Light begins from here. Correct. It goes in a straight line, and now here it obeys Snell's law. Right. It should go straight if it was the same medium, but this is a higher refractive index. Lower refractive index, does it go away from the normal or towards the normal?
Which is
Higher to low, away from the normal, right? So instead of going here, it actually bends down farther, right? Again, it goes from higher to lower, bends down again. Okay, and something strange happens as you keep going. No, I haven't reached hyperbolic. Why would it turn back? Why would it reflect? We're talking about refraction, right? Why would it reflect back? Would it reflect back? Because, very good, because it reaches a critical angle. There is a critical angle beyond which there is no refraction. Is that all familiar? That's called total internal reflection, right? So eventually, you keep increasing your angle, incident angle, you cross that refractive. Now there is no refraction, it reflects. when it goes back up, it's going from lower refractive index to higher. So it bends towards the normal, bends towards. If I did this all correctly, this will be all symmetric. Okay, that's not very nicely done, but that's how it is. Okay, so for all our purposes, this actually happens continuously. This goes like this. Okay, I simplified it for making it stratified medium, layered medium, but it goes like this. And let us say there was a tree here. I got a human standing there. There is a tree here, and there is an eye here as an observer. An observer interprets any two rays that is coming in. We have no idea of this path light is taking. Like, we have no idea. What we do is we take two rays, project it backward. Wherever they meet, that's where we think the object is. So this eye, this observer, has no idea that light is coming from there. As far as the observer goes, it will project it straight down, and there is another light that is coming in from straight down here. There is another light coming here. Wherever they meet, or you can say this is the light, right? Wherever they meet, that's where the image is. So instead of seeing this human here, they will see an inverted image of a tree or a human there. And we think that whenever there is something inverted, that must be a reflection. Right? Again, training, right? We don't expect humans to walk around inverted. We don't see trees inverted. So we think that, oh, there must be a reflection there. There must be a glass there or water there. So most of the time, the illusion is, and there is usually this atmosphere, as I said, it's really small, 1.00. This is the fourth decimal that you're changing it. So this variation is really small. So there is a shimmering feel here, because even a little bit of movement of the atmosphere, hot and cold, this will make this move, and it looks really like water. Okay, so that's mirage, and the idea is that if you're in a desert, it's very, especially if you're very thirsty, then the illusion takes a bigger claim on you, or bigger effect on you, and you really start imagining. More recently, I came across the fact that now this is hot to cold, right? So on a very cool day, right, to have the feature that you have a very cold day, right? This is cool day, like these days, right? Recently, we had 2 weeks back, you had a very, very cold day. And on that day, refractive index now is in the opposite direction, right? So refractive index N increases with or decreases with temperature. So refractive index goes this way. Right? Here it was high, so here the refractive index was increased. Right? Right now, the refractive index is decreasing. So again, what will you think about is that instead of rays going this way, you can imagine a situation where
When the person is attending.
yeah, I'm thinking how to see this. I think you can think of a ray diagram like this. Okay, so there is an object here. So typically how it works apparently is that this is, let's say, water, right? And let's say there is a ship here, right? So light starts from the ship, and this is an observer here, right? And light should come in here, but again, we don't realize that water is, light is coming as a curve. We project it upward, and we think that light is coming from here. So you'll see the ship floating in air, right? And there are pictures that have been taken recently, and you'll see this. Look it up quiz, right? Look this up. Mirage on a cold day, maybe. I don't know what to search for. So, but I've seen pictures of this, and earlier I didn't believe it, but then when you see this explanation, it makes sense. And so this is the opposite of a mirage. So on a cold day, very cold day, you can see things floating around. But the broad difference between this and that is that the refractive index is continuous, right? That's what we want to deal with. And we won't keep it like this because refractive index is in this direction, right? The way we picturized here, we had the refractive index horizontally. So let's change the problem and let's have first, right? So this is x naught. That's x1. That's x2. And let me keep going. This is n1, let's say, and that's n2. It keeps going. If I make this very close, then it becomes continuous. I'll very quickly make that continuous, but let's first do it the discrete way. This is a this will be called a stratified medium, right? Stratified basically means layered medium. So we have exactly the same problem, but now we have more than one. So again, if I start from one point, so x dot, y naught, this I keep it fixed. Okay, so this is fixed. And somewhere at the very end, right, at the very end, this is also fixed. Like it has to reach here. To state the problem, I have to fix 2 points, correct? And this will be a common feature we will always see, even in the trajectory. In Newton's law, you will say initial conditions are fixed, right? I have to start from somewhere, right? Either I should say initial position and initial velocity, or initial position and some final position. So that's that will be the feature of that. Now here, the light can go various places. I can say that light goes here, here, here. Of course, it probably will go smoothly. This will be x1, y1. x1 is fixed, so y1 is the variable. x2, y2. The time taken will be t1, t2, t3. So the time taken to go from initial position to the final position depends on y1, y2, and so on. Correct. So y1, earlier it was just y1, now it is y1, y2, and so on. This one will be t1, or it is n1, right? So c times, so that is a c multiplied, so that I have n1 times s1. Let me first write it in a simpler way. So this is nothing but t1, time taken to go from here to here. That depends only on y1. Plus, let's say, time depends on y1 and y0. Plus t2 depends on y2 and y1. Plus so on. Clear? Questions? Okay. This is nothing but distance x1, y1, y0 over v1 plus s2, y2, y1 over v2, and so on. Multiply by a c times t, c, and this becomes, now I have c times t, which depends on y1, y2, and so on, is equal to n1 times s1 plus n2 times s2 plus so on. And again, s1 depends on only the first two variables, y1 comma y0, y2 comma y1, and so on. If I want to minimize this time now, what are the conditions? Earlier it was derivative with y1 has to be 0, and now I had to minimize with y1, I had to minimize with y2, and so on. So the conditions are more now. So I have to, so the minimum Fermat's path, or the minimum path will be take the time derivative of with respect to y1 is equal to 0. Take the time derivative with respect to y2, that will be equal to 0, and so on. Y3 is equal to, and so on. Okay. Suddenly, you have a multivariable quantity that is coming in. Earlier, there was one variable. I took the derivative of that. That's set to 0. I have many variables, so it seems like it might be appropriate to define a vector. Right, a vector as y is equal to y1 times some unit vector e1 plus y2 times some unit vector e2 and so on. Okay. If that's the case, how do I write this quantity? I want to write the derivative of y1, derivative of y2, all of them are 0. I want to write it in terms of this vector. What is the familiar thing that you've studied, which lets me write all those as a single equation?
Gradient.
Very good, right? So immediately I say I will also define a gradient will be E1 d by dy1 plus E2, a very generalized gradient, not the typical spatial gradient. So this is an n-dimensional, or very quickly we are going to, when it's continuous, it's going to be infinite dimensional gradient, right? Because if it's a continuous variable, it has infinite dimensions. So my conditions for Snell's law is gradient of t times t, which depends on this vector y1, right? Vector y, instead of writing y1, y2, y3, I say y, has to be equal to 0. Right? So if I were to do that, let's very quickly do that. And then this taking this derivative is what you're going to study in the next lecture. But let me do this generally for this layered system. It's straightforward. Let's say first let's do d by dv by 1, right, of c times t has only a derivative with here. Y1 shows up only in these two terms. Next term doesn't have y1. Right? So this is nothing but n1 is a constant, and d by ds1 over dy1 plus n2 d by ds2 over dy1. Right? That is nothing but, if using that feature, this is, we have to set this to 0. That's n1 sine theta 1 minus n2 sine theta 2. We already did that before. If you do time derivative with respect to y2 of ct, again set that to 0, that will come out to be n2 time derivative of s2 with respect to y2 plus n3 time derivative of s3 with respect to y3. Nowhere else you see y3. Oh, sorry, y2. Y2. Nowhere else you see y2. This will give you 0 is equal to n2 sine theta 2 minus n3 sine theta 3, and so on. Okay. So the conditions now, if I want to write this, the set of equation will be ni sine theta I is equal to ni plus 1 sine of theta I plus 1. That's clear. I generalized it very quickly. I kind of made a leap, but the idea is there, right? In there. How many equations are there in this? If there are, let's say, 15 layers here, like 1, 2, 3, so on. How many equations are there in this? 15 equation for at each interface, there is a condition, right? Snell's law at each interface. First interface, Snell's law. Second interface, Snell's law. Only thing N1, N2 changes. And then N2 and N3, N3 and N4, and so on, right? All those things we want to capture, right? Now we want to do the same thing with a continuous system. Okay, so let's, in the last 7 minutes, let me go back and think about gradient, right? Let's say we have a function t, just because this is t, doesn't have to be, right? It's a function dependent on a vector y. This time you can think of it as a spatial vector, perfectly fine. Let's say this is equal to y dotted with a constant a. Okay. If you're familiar with index notation, you will say this is equal to yi times ai. Is that clear? Good. I want to take the gradient of this function, gradient with respect to y. So just because we are used to, I think, gradient with respect to x. So this is gradient with respect to y of t would be equal to gradient, right? With respect to y of y dotted with a. Notice this is dot product of these two quantities, right? What is this equal to? What is this equal to? It's a tensor, good, very good. And what is that tensor equal to? A very special tensor. Maybe this is written in terms of y, gradient of r, right? R is nothing but the same vector, right? In position space, in electrodynamics. That one, very good, right? This is one, very good. Right? In index notation, you will say this is 3 vectors x I, let's say, of another 3 vectors xj, that's delta ij. Right, very good. Right, so that's 1 multiplied by a, that's 8. Okay, so keep that in mind. See, that is it's very straightforward actually what we are doing. This is nothing but y1 a1 plus y2 a2 so on. It's just bookkeeping. Derivative with respect to y1 is a1, right? The first component. Derivative with respect to y2 is a2, the second component. Derivative with respect to y3 is a3, the third component, and so on. You're not doing any sophisticated stuff. But now we want to make a leap here. This is discrete. y1, y2, y3 is discrete. I want to make this continuous. And how do I do that? So for this on 3 minutes. So I have t of y, instead of writing that as a vector, I say yi, right? I is discrete. This is equal to yi ai, right? Same idea, where I is equal to 1, 2, 3, so on. This is basically a sum, right? y1, a1 plus y2, a2, so on. Right? And I said derivative of this is just the first component, second component. This is a summation when this is discrete. I can say instead of an I, I'm going to have a variable which is continuous. I has been upgraded to X. I was 1, 2, 3. X is real, right? It's less than B and greater than A, real. You can take all decimal values, right? It's a real number, right? So instead of I upgraded it to a function. Right? How many, this has 5 or 6 components. This is infinite components, right? It's a continuous variable. This is a summation. Summation in a continuous variable gets upgraded to integral, right? So now I have to do an integral, right? dx of y of x and a of x. An integral will have a limit, let's say alpha to beta or s1 to s2, right? Some values of. Now I have to talk about derivative of this variable dt with respect to a certain value of y at a certain point, right? Let's say x prime. Okay, that's what we want to work with. Okay, that's the generalization of it. And we will do that next time. Okay. This will be called a functional derivative. Quiz, read about that. Functional derivative. That's all. Thank you.